Hello everyone, welcome to the presentation of our work entitled Weakly Supervised Audio-Visual Sound Source Detection and Separation. Sound source separation is an important and well-defined problem which stems from an observation that one can attend to a single conversation even in a crowded room with many parallel conversations in progress. This phenomenon is known as the cocktail party effect. The cocktail party effect illustrates humans' innate ability to selectively attend to sounds from particular sources. Building automated systems that do the same is not only scientifically interesting but also has an endless set of practical applications ranging from audio denoising to speech recognition. Recent approaches to sound source separation rely on visual in addition to auditory signals to improve the performance. In the cornerstone ECCP paper by Zhao et al., authors propose a pixel player to separate the accompanying audio into components and spatially localize these sources in video. Their method leverages mix and separate framework for training, which was then adopted by many following works, including our own. The idea is to generate an artificially complex auditory signal by mixing multiple individual audio signals and learn to separate each individual sound of interest from the composition with video as context. However, fundamentally, the approach is not able to localize individual objects when multiple such objects in a single source video produce sounds. To address this, more recently, Gao et al. Proposed a co-separation framework. These work enforce separation within a single video at the object level with the use of pre-trained object detector. However, this implicitly assumes existence of object instant annotations on an external dataset. Our main contribution is an audio-visual co-segmentation approach for sound source separation, where the network learns both what individual objects look like and sound like from videos labeled with only one or more object labels. It can be learned in an end-to-end manner and requires no additional supervision or bounding box proposals. On a technical level, we formulate spectrogram mask prediction using a set of learned mask bases which are combined using sparse coefficients, condition, or multimodal features. We will now overview our approach which uses mix and separate framework. Given two input videos with accompanying audios, we detect and segment objects that make sound from each video using a weakly supervised segmentation network. At the same time, we generate a complex mixed auditory signal by mixing two audio signals. Then we use an audio separation network to separate individual object sounds. Here is the detailed architecture of our proposed end-to-end audio-visual network. Our architecture has two paths. First, a video frame semantic segmentation path designed to detect objects that have potential to make sounds and segment them out in the frame. Second, a spectrogram mask prediction path which takes both mixed audio and pooled object class image features and output a dense mask. The input to the frame segmenter is a RGB frame. We use ResNet 18 as backbone network followed by convolution to extract visual features and feed to weakly supervised segmentation network to detect and segment objects. For audio, we use time frequency representation of sound. Therefore, first we apply short-time Fourier transform on the input mixture sound to generate corresponding spectrogram and feed to the attention unit. We utilize an attention unit architecture to first dynamically generate auditory mask bases from the mixed spectrogram itself. We then generate coefficients for these bases conditioned on multimodal features. The final mask is constructed as a coefficient weighted combination of predicted bases. Our weakly supervised frame segmentation network itself contains two branches, expensive attention detector and discriminative attention detector. Expensive attention detector identifies object regions and generates expensive attention map. Discriminative attention detector predicts the discriminative parts and generates discriminative attention map. Finally, we combine both attentions and generate final attention maps using element-wise multiplication. The attended feature is passed through a spatial average pooling layer to generate classification score for corresponding class. We then apply a multi-level classification loss to train the network. We note that class-specific attention maps learned in this way can be interpreted as localizations of potential objects that could make sounds. We use attention unit to extract audio features from the log magnitude of a spectrogram. The final output of attention unit are audio mask bases using K channels. The goal of mask coefficient generator is to predict k mask coefficients. The mask coefficient generator consists of a series of convolution layers with nonlinear activations and batch normalization. We predict final magnitude of a spectrogram by linearly combining audio mask bases from attention unit with the mask coefficient. Then we use the inverse short-time Fourier transform to get a waveform of the prediction. Our ultimate goal is to learn spectrogram mask of two types, binary or ratio. Binary mask effectively corresponds to hard attention, while ratio mask is soft attention on the spectrogram bins. We conduct experiments on two datasets, music and audio set single source dataset. Music dataset contains 685 untrimmed videos of musical solos and duet. On the other hand, audio set single source is a small dataset which we only use for evaluation. Consistent with prior work, to reduce the computational cost, we subsampled the audio signals to 11 kHz and compute short-time Fourier transform to generate time-frequency audio spectrograms. To measure performance, we use three widely used metrics for sound separation: signal-to-distortion ratio, signal-to-inference ratio, and signal-to-artifact ratio. The table shows experimental results on music dataset using both binary and ratio mask. We also include sound separation results with and without weakly supervised frame segmentation network to show the importance of that module in our architecture. This table shows accuracy of our object detection network by computing multi-class classification accuracy on the music test set as a function of different threshold value. Results illustrate that we can achieve high accuracy of up to 93.69%. We also perform cross-dataset testing to evaluate the generality of our method. We do so by measuring the performance of our proposed model trained on music dataset by applying it on audio set single source dataset. We also conduct a small experiment to see how the models perform in separating objects that they have not seen during training. More details on this experiment can be found in the paper. Now we will see some qualitative results. Here is the input mixed spectrogram with corresponding audio before separation. Here you can see separated spectrogram and corresponding sound of violin obtained using our method. And here is the separated spectrogram and sound of acoustic guitars. We also qualitatively visualize results from our weakly supervised segmentation network. As can be seen, our network correctly focuses on the instruments that generate sounds. To conclude, in this work, we introduce an end-to-end audio-visual co-segmentation network to separate and detect sound source without requiring additional supervision on bounding box proposal and solve the problem in a weakly supervised manner from large-scale unlabeled videos. Both quantitative and qualitative results across dataset and variety of settings show the effectiveness of our proposed method. Here are some references used in this presentation. Thanks to all.